All right, guys, let's start. Today's lesson is going to be about thermodynamics. Before we start and give you the definition for what thermodynamics is, what does thermo mean, guys? Heat. And dynamics just means moving from one place to another. And so what thermodynamics means, please write this in your guided notes. Thermodynamics is the study of energy and its interconversions. It's the study of energy and its interconversions. We talked about this last time, but can you create or can you destroy energy? No, there's this thing called the law of conservation of energy. You can't create it, can't destroy it, but it can change forms, or it can be converted from one form to another. And that's what thermodynamics is. So we're going to start into looking at how heat or energy can be changed from one form to another. Okay, there's a few laws in thermodynamics. The first law says that energy of the universe is constant. So the energy in the universe is constant. Because we can't create it. It's not like all of a sudden tomorrow there's going to be more energy than there was before, right? And we can't destroy it. So the energy in the whole universe is constant. But that energy in the universe can change forms from one thing to another. Here's kind of the main topic of today's lesson. It's called internal energy, and it's given this symbol capital E. Internal energy is the sum of the kinetic and potential energies of the system, which is, in chemistry, we're talking about the chemical reaction. So it's the total energy of the system. It's not considering the surroundings. We're only going to be concerned about what's happening with the system. So that's internal energy. It's given the symbol of capital E. Well, energy can pass between the system and the surroundings in two ways. As heat, which we talked about in the first lesson. Did we tell you that the symbol for heat is Q? So guys, when you see Q from now on in this chapter, you're thinking heat. That's what it means. Well, energy can either pass between the systems and the surroundings either as heat or as work. And work is given the symbol W, which makes sense. Most of the time when we're talking about chemistry, we're talking about energy transfer in the form of heat. But there is an application in chemistry for work, and that's what we're going to talk about today. But most of the time when we're talking about energy in terms of work, we're talking about physics. Okay, but today we will talk about it in terms of chemistry. All right, this equation we are going to use all day. Make sure we know that. I'm going to point to the variables of this equation. I want you to tell me what it means. What is this? Yeah, it's a Greek letter delta, which looks like a triangle. What does it mean, though? Change. So somewhere in the margins of your books, let's put equals change. Okay, that's a good description. But when it's in an equation, how do we calculate change? I also want you to put this. How do you calculate change? It's always final minus the initial. Final minus initial. Doesn't that mean change, guys? In a quantitative sense, when you're calculating it out, you're going to take the final, whatever it is you're talking about, minus the initial. And that's how you calculate change. Okay, so that's what delta means. What does E mean? Internal energy. Are we talking about the system or the surroundings when we see that? The system. So this is the change of energy in the system. Is equal to. Now there's two ways that heat or energy can be passed between the system and the surroundings. It's Q. What's Q? Heat, or W, which is what? Work. Okay. So the internal energy of the system can change either by heat flow or by work flowing in or out. Okay, let's go back to the definition of what the universe, the system, and the surroundings, and kind of look at that. The universe is divided into two halves. Okay, there's the system, which in chemistry, the system is the chemical reaction. Or there's the surroundings, which is everything else besides that chemical reaction. This is good review. Exothermic reactions release energy to the surroundings. So energy is leaving the system and going into the surroundings. That's why it's called exo, which means exit heat. There's endothermic. Endo means enter. Again, thermic means heat. If heat is entering, then it's being absorbed from the surroundings. So it's coming into the system. Now we're going to look at it more quantitatively, which means we're going to put numbers to it. So we need to know how to measure energy. Every energy measurement has three parts to it. Number one is a unit. So the unit for energy is called what? A joule. A joule, which is abbreviated capital J. Or you might be more familiar with another unit of energy, which is called calories. Almost everything we eat has a nutrition facts label on it. You can look at how many calories there are in that certain amount of food item. And that's a way to know the amount of energy that it contains. Well, these are both units. We're going to use joules because that's the SI base unit for it. But if I give you calories, is there a way to convert to joules?
Yes.
Yes. And if I give you joules, is there a way to convert to calories?
Yes.
Yeah, we just use a conversion factor, which I will give you. Okay, so there's three parts to an energy measurement. First is a unit. Second one is a number. Obviously, we need to know how many. So that's the magnitude, the number. And number three is a sign. Now this one is where students will get confused. The sign tells the direction of energy flow. If it's negative, that means it's leaving the system. So if it's leaving the system, it's exothermic. It's leaving, it's going to be negative. But if it's coming into the system, it's endothermic. The sign is going to be positive. So anything coming into the system is going to be positive. Anything leaving is negative. Remember, we always take the system's point of view. So if it's coming into the system, it's positive. If it's leaving, it's negative. Okay, let's look at exothermic reactions. We've talked about this a lot, but if energy here is leaving the system, the internal energy is going to be positive or negative if it's leaving. Negative. So it's less than 0. This is a less than sign. And so it's a negative sign. Okay, just the opposite for an endothermic reaction. If energy is coming into the system, remember we take the system's point of view. So if it's coming into the system, is it going to be positive or negative? Positive, which means that the internal energy of the system is greater than 0. This is a greater than sign. Okay. Just to review. Hey, we're going to use that notation a lot. What does this mean, guys? Greater than. What is this sign? Less than. Okay, we have to keep that straight. Okay, so let's go back to that equation that we're going to use today. The change in internal energy is equal to heat flow plus work. Well, here's some rules for heat and work. Number one, heat given off is negative. So if heat is given off, it's leaving the system, so it's going to have a negative sign. So Q will be negative if it's given off. Heat, if it's being absorbed, it's coming into the system, then it's positive. Okay, now let's talk about work. We haven't talked about it yet, so let's pay attention to this part. Work done by the system on the surroundings is negative. So if work's being done on the surroundings, work's leaving the system. So again, if it's leaving the system, it's going to be negative. Always keep the system's point of view. Now, what if work is being done on the system? So now it's being done on the system, so it's coming into the system. It's going to be positive. Always take the system's point of view. Okay, let's introduce work, and then I've got a few practice problems concerning work. So, in physics, work is a force acting over a distance. So if I have a box here, and I wanted to move it, well, I would need to put a force on it. And I would move it, I don't know, a distance. So if this is my force, in physics, we would calculate that by taking the force and timesing it by the change in distance. You're doing work on it, right? So you have to put a force over a distance. That's the physics definition. But in chemistry, work is defined this way. Please write this down. In chemistry, work is equal to a negative P, this triangle again, and V. So let's go over what these mean. What is W? Work. It's equal to a negative, what's P? Pressure. Yeah, remember the gas law chapter. P is for pressure. What does this triangle mean? Change. Which, how do we calculate change? Final minus initial. And what does V stand for? Volume. Okay, so good. So work can be calculated by multiplying the pressure by the change in volume. The units for work, if you calculate it this way, what's the units for pressure? ATMs. What's the units for volume? Liter. So we just call it a liter atmosphere. Those are our units for work. Okay. Work is done by a gas through expansion, or work is done to a gas through compression. I'm going to put a little star by this one. We have to think about that for a second. Let me see if I can draw a visual, kind of a balloon here. It's not very blown up, but then let's say we blow up the balloon here and it expands. Okay? So work is done by a gas through expansion. So now work is, if it's expanding, work is being done by the gas. But what if we compress the air? What if we compress that air and the volume shrinks? Now work is going the other way. And so it's going to be kind of tricky to figure out the sign notation here. But stay with me, we'll get through it. Okay, if the volume of a gas increases, the system has done work on the surroundings. If the system does work on the surroundings, do you think it's going to be a positive sign or a negative sign? If the system is doing work on the surroundings. So it's leaving the system, it's going to the surroundings. It's negative, okay? So work is negative in that case. So again, let me draw that balloon. So if it expands, work is negative. If it expands, work is negative. And we can see that if we look at this, equation here. Work is equal to a minus pressure times change in volume. So now we're going to do, what we're really saying there is volume final minus volume initial. And if the initial volume is pretty small, like it is right here, see how this would be a pretty small number? And then if the final volume is large, like it got larger volume, so you have a big number minus a small number, it's going to be positive, right? This sign will be positive here. But with this equation, you always have this negative sign out front. So that's what makes work negative. If it expands, work is negative. So let's contrast that to the opposite. What if the volume is compressed? What's the sign of work going to be? Okay. So let's look at it. If gas compresses, surroundings do work on the system and work is positive. Good. So now if we take the opposite of that, if we have this huge balloon and then over time we compress that, work, the sign of work is going to be positive. So if the balloon expands, it gets really to a greater volume, work is what? Negative. What if we compress that air? Work is positive. Now, because we're talking about energy, we want the units to be in joules. But if we find work this way, our units are going to be atmospheres per liter, atmospheres liters. So to convert between liter, atmospheres, and joules, we're going to use the following conversion factor. Please write this somewhere in your guided notes. Is it there? Okay. 1 liter atmosphere is equal to 101.3 joules. Guys, a joule, I don't know if I explained this, a joule is a really small unit. It's a small energy unit. Okay. Let me see if I can explain what a joule is. Okay, 1 joule is the amount of energy it takes to raise the temperature of 1 milliliter of water 1 degree Celsius. 1 mil of water is very small, right? How much energy would it take to raise that 1 milliliter of water 1 degree Celsius? Not that much. And so a joule is a very small unit. And so a lot of times in these problems, you're going to see the units in kJ. What does kJ mean?
Kilojoules.
Kilojoules. So you just times it by 1,000, you get kilojoules. Okay, I've got some practice problems. Number 6. Let's go through it together. It says, calculate the delta E for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. Okay, let's break this down. Calculate delta E. We need an equation for delta E. What is it that we just learned?
Q plus.
Good. Delta E is equal to Q plus W. So the change in internal energy of the system is equal to Q. What's Q?
Heat.
Heat plus
Work.
work. Good. Okay, it says that it's an endothermic process, guys. What does that mean? Is heat coming into the system or is heat leaving? It's entering. So is heat going to have a positive or a negative sign?
Positive.
Positive sign. How much heat came into the system? 15.6. So that's my Q. So I'm going to put 15.6 kilojoules in for Q. Okay, so we're going to add that to whatever W is. Let's find out what W is. And it says 1.4 kilojoules of work. Now be careful with the wording here. Is done on the system. So it's being done on the system, which means it's coming into the system. Is it going to be positive or negative?
Positive.
Positive. So all we have to do is take that 1.4 kilojoules and add it to the 15.6 kilojoules, and that will tell me what delta E is equal to. So if you do that, what is delta E?
17.
Yeah. 17 what? Kilojoules. And it's positive. So now does the chemical reaction have more energy now? Yeah. It gained energy in the form of heat and work. And so now it has more energy. Now, can we just create that energy from nothing?
No.
Where did it come from?
The surroundings.
The surroundings. Yeah. And the universe stayed constant. Yeah, that first law of thermodynamics, the energy of the universe stays constant. Okay. And so, yeah, we got it right. Okay, let's go to number 7. Practice problem number 7 says, calculate the work associated with the expansion of a gas from 46 liters to 64 liters at constant external pressure of 15 atmospheres. I always like to draw a picture of what's going on here. So we have, I don't know, a gas, It was at 46 liters. And then it expanded. So it got larger and it expanded to 64 liters. Okay, we're calculating the work. How do we calculate work? What's that equation with work in it?
Work equals V.
Good. Okay, that's how we calculate work. Let's write that equation down. Now let's just plug in our variables here. What is P? 15 atmospheres, right? That's a pressure, so 15. Now, you always have to use this negative sign out front. You have to keep it there. It's just built into that formula, so keep it there. Now, delta V, how do we calculate delta V?
Final minus initial.
Final minus initial. So let's times the, what's final?
64.
Final was 64, so we're going to put 64 right here, minus the initial of 46. Okay, that's it. So let's throw that into the calculator. Are you guys getting negative 270? Okay. So work is equal to a negative 270 what though? Remember, we got to have a unit. What's pressure measured in? ATM. What's volume? Liters. So we just call it a liter atmosphere. A liter atmosphere. Could I convert this to joules if we wanted to? Yeah, we could. So let's go back. I said that all energy measurements have three parts. They have a sign. If it's negative, is work being done on the system or on the surroundings? On the surroundings. So it's leaving the system, it's going to the surroundings. And it has a number, which tells us the magnitude, 270. And it's got to have a unit, liter atmospheres. So there's the three parts. Hey, good job. Minus 270 liter atmospheres. Very good. Okay, last practice problem. I wanted to work through this one with you. This one's a little complicated, but it's just combining the last two practice problems. Let's see if we can combine those two. Okay, practice problem 8. Let's read it. A balloon is being inflated to its full extent by heating the air inside of it. We saw this in the gas law chapter, right? If you heat air, what happens to its volume? It expands. The space between the air molecules gets larger. That makes the volume expand. Okay, it says, in the final stages of this process, the volume of the balloon changes from 4 times 10 to the 6 liters to 4.5 times 10 to the 6 liters. So it expanded by the addition of 1 times 10 to the 8th, 1.3 times 10 to the 8th joules of energy as heat. So of course we've got to heat it up for that expansion to take place. That's the measurement of heat that they added to it. Assuming that the balloon expands against a constant pressure of 1 atmosphere, calculate delta E. Okay, so we need to calculate delta E for this process. Let's first start by drawing a picture of what's happening here. Okay, here's my balloon. It was at what volume to begin with? 4e to the 6th liters. Okay, we're heating it up. I don't know, I'm going to draw a little candle under here. It's heating it up, okay? And it's going to what volume? 4.5 e to the 6. Okay? That's kind of a picture of what's going on. What do we call this candle? I mean, it's heat, but what is it really? What's the symbol for heat? Q. So I'm going to put Q is equal to, how much heat did we add? 1.3 times 10 to the 8th. So I'm going to put that here, 1.3 times 10 to the 8th joules. Okay, so that kind of is a picture. It helps me visualize what's happening. Let's go back to this. Calculate delta E. What's the equation for calculating delta E? Good. Delta E is equal to Q plus W. Heat plus work. Now let's see if we can plug it in and just solve for it. Okay. Do I have Q? I do. It's 1.3 times 10 to the 8th. Now, it's being added to it. So is it going to be positive or negative? If it's coming in. It's being added, so it's positive. 1.3 e to the 8th joules. Now all I have to do is add in work here. What is the work? Did it tell us? No, but we have pressure and volume. Can I find it? What's that other equation for work? Times delta V. Good. A minus pressure times delta V. Let's plug in and see if we can get an answer for what work will be. What is pressure in this case? 1 atmosphere, so I'm just going to put in 1 right there. Now we have to keep this negative sign, that's just built into the equation. Now delta V, how do you calculate delta V? What number comes first? The final volume. What was the final volume? Good, 4.5 e to the 6th. Minus its initial volume was 4 e to the 6th. And this one's measuring in liters, but we'll take care of the units in a second. Okay, what does that equal?
Negative 500,000. Or if you go to science, I don't know what that is.
Isn't it 500,000 going right there? So 500,000 right here. And if we times that by minus 1, isn't the work equal to a minus 500,000 what? What are my units if I solve it that way? Is it joules or is it liter atmospheres? It's liter atmospheres. Okay, well that's a problem. How come? Because my heat is measuring in what units? Joules. Can I add joules to liter atmospheres? So can I just put that negative 500,000 liter atmospheres right here and add it to joules?
No.
No. You've got to convert it to like units. Let's go to joules, okay? How do I convert that to joules? Well, here's my conversion factor. So let's put this over 1 and convert it. If liter atmosphere is on top, guys, where does it got to go? On the bottom. So let's put liter atmospheres down here. And what's my conversion factor? 1 liter atmosphere, so I'm going to put a 1 down here, is equal to what? 101.3 joules. Yep. So let's times that negative 500,000 times 101.3. Do you guys get this? Let's put it in scientific notation. So work is equal to minus 5.065 times 10 to the 7th joules. Did you guys get that? Okay. And now that we have it in joules, we can put that in over here for work. A minus 5.065 times 10 to the 7th. Let's just add those two numbers together now. Okay, so I'm getting this for delta E, it's equal to I'm going to put it in scientific notation because it's such a large number, times 10 to the 7th. And what's my units? Joules. Yeah, it was negative. So you have to take this one, though, the heat, Q, and add it, which is really subtraction in that case, right? So subtract the work. Don't you guys get this number?
Yeah.
Okay. Let's talk about what that means. Delta E is the change in internal energy, which means it's the energy of the what? System or the surroundings? System. Okay, it must have increased by 7.935 times 10 to the 7th joules. Okay. Very good. So that's kind of combining all the stuff that we learned today. Before I end the video, let me just review. If heat leaves the system, is it going to be positive or negative? Negative. If it leaves, it's negative. What if heat comes in? Positive. What if work is being done on the surroundings? So work is leaving the system and going to the surroundings. It's negative. What if work, obviously, if it goes the other way? So what if the surroundings do work on the system? It's positive. Okay, always take the system's point of view. We talked about two equations in this video. The change in internal energy is equal to Q plus W. What is Q? Heat. What's W? Work. And we also figured out how to calculate work in terms of chemistry, which is what, guys? Negative P times what? Delta V. And whenever you see delta, it's what? Change. So how do you calculate change? Final minus initial. So, good. Hey, now that we've learned that, there is some more practice for you in your student workbook. Please go to your student workbook and I want you to complete the first Law of Thermodynamics worksheet. Before I end it, what is the first law of thermodynamics? Energy of the universe is constant. Okay? So go there and complete the first law of thermodynamics worksheet, and hopefully this video helps you.